In this lesson, we're going to explore the reactions of dienes and alkynes, electrophilic additions to molecules with multiple carbon-carbon pi bonds. Dienes are just molecules that have two alkenes, and because they're alkenes, they undergo the same electrophilic addition reactions. In a conjugated diene, the two alkenes are separated by one single bond. This creates a contiguous chain of four sp2 hybridized carbon atoms. Because dienes have two alkenes, each diene molecule could potentially react with two molecules of an electrophile. We describe that as reacting the diene with two equivalents of an electrophile. An equivalent is just an equimolar amount relative to the reactant. In the reactions of conjugated dienes, we're going to restrict the reactions to using one equivalent of the electrophile. When a conjugated diene is treated with one equivalent of an electrophile, like HBr, it can form two possible products. The first is the expected Markovnikov regioselective addition of the HBr molecule to either of the two alkenes. This is called the 1,2 addition product, because the H and the Br were added to adjacent carbons, or 1 and 2 relative to one another. The second product is likely a bit of a surprise. If you look closely, you can see that the hydrogen and the bromine were added to the opposite ends of the conjugated pi system, placing a double bond in between the double bonds of the reactant. This product is called the 1,4 addition product. If we arbitrarily assign the carbon that bonded to the hydrogen as carbon number 1, we can see that the bromine attached to carbon number 4, and that's why it's called a 1,4 addition product. The mechanism for the reaction is exactly the same as the reaction for an alkene with HBr. The first step is to protonate the alkene with the strong acid to form the most stable possible carbocation. Protonation of a conjugated diene can result in the formation of a resonance-stabilized allylic carbocation. In the allylic carbocation, the electron deficiency is shared over two carbons, and that means that this single carbocation actually has two carbons that are electrophilic. In the second step, the bromide acts as a nucleophile and can attack either the secondary carbon following the red curved arrow, which makes the expected 1,2 addition product. The bromide could also attack the primary electrophilic carbon following the green curved arrow, leading to the unexpected 1,4 addition product. It's important to recognize that in this reaction, only one carbocation is formed. The bromide isn't choosing to attack one carbocation over another. Rather, it is choosing to attack one carbon over another in that resonance-stabilized allylic carbocation. So which product is the major product? Well, it turns out that both products are actually favored, which admittedly is kind of like having a brother or sister and your parents saying, "Oh, you're both our favorite." So to see why both products are actually favored, we need to do an analysis of the energy changes that occur during the reaction, and that means a thermodynamic analysis and a kinetic analysis. So here is a free energy diagram of the reaction. A thermodynamic analysis of the reaction shows that the 1,4 addition product, here shown in green, is actually more stable than the 1,2 addition product, shown in red. If we look closely at the two products, we can see that the 1,4 addition product is a di-substituted alkene, and the 1,2 addition product is a mono-substituted alkene. And it turns out that alkenes are more stable when they're more highly substituted. And so the more highly substituted 1,4 addition product is the more stable product. And that means that at equilibrium, the 1,4 addition product in this case is going to be the major product. When we do a kinetic analysis of this reaction, we get a completely different result. You can see that the first step in this reaction is the slowest step, and so it's the rate-limiting step. But the rate of that step doesn't actually affect which product is favored. And that's because both products come from the exact same allylic carbocation formed in that first step. Which product is ultimately formed in the reaction is actually determined in the second step, and that's why it's referred to as the product determining step. If we look at the free energy diagram, we can see that the red pathway, which leads to the 1,2 addition product, is actually faster than the green pathway, which leads to the 1,4 addition product. As the bromide approaches the allylic carbocation, it will be attracted to either of the two electron-deficient carbons. If the bromide approaches the secondary carbon, then the transition state that forms will closely resemble a secondary carbocation. If the bromide approaches the primary carbon, then the transition state that forms will closely resemble a primary carbocation. And we know that secondary carbocations are more stable than primary carbocations. And by Hammond's postulate, that means that a transition state that looks a lot like a secondary carbocation will be more stable than a transition state that looks an awful lot like a primary carbocation. And that makes the red pathway, leading to the 1,2 addition product, the faster reaction. And that means that the 1,2 addition product is favored kinetically. And that's why both products of this reaction are favored. In this case, the 1,4 addition product is more stable and therefore favored thermodynamically, and the 1,2 addition product is formed more quickly and thus favored kinetically. Well, that doesn't actually answer the question of which product is the major product. And that is going to depend on whether the reaction is run under thermodynamic control or kinetic control. The thermodynamic product is the more stable product, and it's going to be favored by anything that promotes equilibration. And one thing that can promote equilibration is to have a high reaction temperature. The overall reaction here is exergonic, and that means that the products are more stable than the reactants. In order for the reaction to go backwards, more energy is required than in the forward reaction. So a higher temperature will provide that extra energy and allow the reaction to go backwards and forwards, favoring the thermodynamic product. In this specific reaction, the 1,4 addition product happened to be the thermodynamically favored product. But that's not always going to be the case. The thermodynamic product is simply the more stable product, and it can actually be the 1,2 or the 1,4 addition product. We just have to look at the two products and decide which one is more stable. And in these addition reactions to conjugated dienes, the more stable product will be the one that has the more highly substituted alkene. The kinetic product is the one that forms more quickly, and to induce kinetic control, we keep the temperatures low. That helps to prevent equilibration and allows the faster reaction to dominate. The kinetically favored product in an addition reaction to a conjugated diene is almost always the 1,2 addition product, and that's due to a phenomenon called the proximity effect. We tend to draw our mechanisms for reactions out kind of linearly with lots of space around each molecule. But you have to remember that in reality, when molecules react, they are literally touching one another. As the pi bond of the diene approaches a molecule of HBr, it starts to break the pi bond and form a CH bond. And at the same time, the HBr bond starts to break. Once the bromide forms, it is very close to the other carbon of the alkene that was protonated. Attacking that carbon will lead to the 1,2 addition product. And it's very fast because the bromide has a very short distance to travel to attack that carbon. In order for the 1,4 addition to occur, the bromide has to travel down the length of the molecule and attack that other electrophilic carbon. And that travel takes time, and it makes the 1,4 addition reaction slower than the 1,2 addition. So the 1,2 addition is faster because of the proximity of the bromide to the 2 carbon relative to the 4 carbon once the bromide is formed. So in our first example, the butadiene molecule was symmetric. Both alkenes were identical, and so it didn't matter which alkene was protonated in the first step of the mechanism. The reaction gets a bit more complicated when the two alkenes of the diene are not exactly the same, and that's because different products will actually be formed based on which of the two alkenes is protonated in that first step of the reaction. Let's take a look at an example. You can see that this diene has two unique alkenes. You can definitely tell one from the other. And that means that the products that will form from an electrophilic addition reaction will depend on which alkene is protonated in the first step. In this case, the reaction is going through an acid-catalyzed hydration, but the process would be exactly the same for a hydrohalogenation. In order to figure out which alkene is more likely to protonate, we compare the stabilities of the allylic carbocations that would form from protonating each alkene. Protonation of the alkene on the left would lead to the formation of the allylic carbocation shown here. And if you look at those two resonance structures, you can see that one represents a secondary carbocation and the other a tertiary carbocation. Protonation of the alkene on the right would lead to the allylic carbocation shown here. And if you look at the two resonance structures, one represents a secondary carbocation and the other a primary carbocation. Because the allylic carbocation that forms from protonation of the left alkene is partially tertiary and partially secondary, it makes it more stable than the allylic carbocation that forms from protonation of the right alkene, which is part secondary and part primary. Because the carbocation that forms from protonation of the left alkene is more stable than the carbocation that forms from protonation of the right alkene, Hammond's postulate allows us to assert that protonating the left alkene will be faster than protonating the right alkene. Once we know which alkene is more likely to be protonated, we finish the reaction as we did before, having the nucleophile, in this case water, attack either of the two electrophilic carbons in that allylic carbocation. If we look at the products of the reaction, we can see that the left product is the 1,2 addition product because the H and the OH added to adjacent carbons, and the product on the right is the 1,4 addition product. Here, the hydrogen added to the leftmost carbon of the pi system and the OH to the rightmost carbon of the pi system. We know that the 1,2 addition product is typically the kinetically favored product because of the proximity effect. The thermodynamically favored product is simply the more stable product. And in this case, the more stable product also happens to be the 1,2 addition product. And that's because the 1,2 addition product is a tri-substituted alkene, and the 1,4 addition product is a di-substituted alkene, making it less stable. So in this case, whether the reaction was run under higher temperatures or lower temperatures wouldn't really affect the outcome. The 1,2 addition product would be favored in either case. Compared to conjugated dienes, the reactions of isolated dienes are really simple. Because electrophilic addition reactions on isolated dienes cannot directly form an allylic carbocation, they're not affected by resonance. The only thing we need to worry about in the reactions of isolated dienes is which alkene will react, at least in the cases where the two alkenes of the diene are unique from one another. The reaction types that we've seen that go through a positively charged intermediate, like a carbocation or a halonium ion, they will prefer to react the alkene with the most substituted carbon. And be very careful with that phrase, because that is often not the same as the most highly substituted alkene. The reason for this selectivity is simply that the more substituted carbon will be able to stabilize the developing positive charge during the reaction. So in this example, we can see we have two unique alkenes in this isolated diene, and the alkene on the right has the most highly substituted carbon of either alkene. The rightmost carbon of that right alkene is more highly substituted than any of the other alkene carbons, and that means it's the alkene on the right that will preferentially react. From there, we simply perform the reaction as we would on a normal alkene. In this case, hydrohalogenation is Markovnikov regioselective, and that means that the bromine will be attached to the more substituted carbon of that alkene and the hydrogen to the less substituted carbon. So we've seen that dienes undergo the same kinds of reactions observed for alkenes, and that's because both dienes and alkenes have carbon-carbon pi bonds, and those carbon-carbon pi bonds are nucleophilic. Well, there's another class of compounds that have carbon-carbon pi bonds, and that's alkynes. And that means that alkynes are going to go through the exact same types of electrophilic addition reactions we saw for alkenes and dienes. In fact, alkynes have a lot in common with dienes, because both types of molecules have two carbon-carbon pi bonds. So let's start with the hydrohalogenation reaction. Because alkynes have two carbon-carbon pi bonds, the hydrohalogenation of an alkyne is sensitive to the number of equivalents of the electrophile that's been added. So here we have one propyne reacting with one equivalent of HBr. Because there's only enough electrophile to react one of those pi bonds, one of the carbon-carbon pi bonds will add HBr, leaving the other pi bond unchanged. We know that hydrohalogenation is Markovnikov regioselective, and so the bromine is placed on the more substituted carbon of the alkyne and the H on the less substituted carbon. The result is called a vinyl halide. It's simply a halogen directly attached to an alkene. Reacting one propyne with two equivalents of HBr allows both of the carbon-carbon pi bonds to react. Here, the abbreviation XS is used to represent literally an excess of that HBr, enough to react all of the pi bonds. In this reaction, one molecule of HBr will react with one of the carbon-carbon pi bonds to form the same vinyl halide we saw above. The vinyl halide will then undergo a second addition, again following Markovnikov's rule and placing the second bromine on the more substituted carbon and the hydrogen on the less substituted carbon. The product, with two halogens on the same carbon, is called a geminal dihalide. The reaction mechanism for the hydrohalogenation of an alkyne is essentially the same as it was for the hydrohalogenation of an alkene. The first step is protonation of one pi bond with the HBr to form a carbocation. Because there were two pi bonds and only one of them reacted, that means that the carbocation will still have one pi bond remaining. This leads to a special carbocation in which the positive charge is actually on an alkene carbon. This is called a vinylic carbocation, and they're relatively unstable. Regardless, the empty p orbital of that carbocation is then attacked by the bromide to finish the reaction. And of course, with an excess of HBr, the reaction simply occurs again, starting from the vinyl halide. Another electrophilic addition we saw on alkenes was the acid-catalyzed hydration, which was the addition of a water molecule across the pi bond. The acid-catalyzed hydration of an alkyne often includes the introduction of a mercury 2+ salt, which helps to further promote the reaction. Remember that the acid-catalyzed hydration proceeds through a carbocation intermediate, and that means it's going to follow Markovnikov's rule. So adding a water molecule across one of the pi bonds results in the formation of an enol, a molecule that is both an alkene and an alcohol. And it turns out that this type of enol is actually rather unstable and undergoes a reaction called tautomerization. You can see that the product of this tautomerization is a carbonyl, specifically a ketone in this instance, and so it's referred to as keto-enol tautomerization. If you look at the structures of the enol and the ketone product, you'll see that they are actually isomers. The hydrogen atom was removed from the oxygen of the enol and placed on the far end of the alkene. The movement of that hydrogen results in a shift in the placement of that pi bond. Because this tautomerization reaction is very fast, the overall reaction is not sensitive to the number of equivalents of water added. So here I show the mechanism of that keto-enol tautomerization. It starts off exactly like the first step in the acid-catalyzed hydration of an alkene. The alkene of the enol is protonated by hydronium, and then a weak base, like water, removes the hydrogen from the oxygen, forcing the electrons to form a new pi bond. The last electrophilic addition reaction we saw on alkenes was halogenation. Halogenation reactions on alkynes are sensitive to the number of equivalents of the electrophile added. And remember that regioselectivity is not an issue in a halogenation reaction, because the same thing is being added to both carbons of the pi bond. So here we have the reaction of 1-propyne with one equivalent of Br2. And you can see that it reacts one of the carbon-carbon pi bonds, adding Br2 across it and leaving the other pi bond intact. Addition of a second equivalent, or excess, Br2 results in the formation of a tetrahalide, with each carbon of the alkyne now bonded to two bromine atoms.